Okay, so we have, I think we've got about 10 examples, and the examples are in such a way that the first few examples, they focus on the first condition of equilibrium, where we have to add up the forces along the x direction and along the y direction, and they have to give us 0. And the other examples, they focus on the second condition of equilibrium. So in this case, for example number 1, in figure 1, the tension in the horizontal chord is 30 newtons. So there is a force which lives in this chord, which is 30 newtons. Tension is basically a force which lives in a rope. So we are told that the force in this particular rope here, the horizontal one, is 30 newtons. Find the weight of the object. So how do you use that to find the weight of the object in this particular case? So what we have is also, it's not only the weight of the object. The weight of the object is what you have down here. So this weight of the object is not shown, but we know that if an object has got mass, the weight points downwards like this. So there is a downward force in this particular direction. However, what you notice about this particular object is that this particular object, with this arrangement which you have here, does not move down and it doesn't move up. So it's just there, it's stationary, it's motionless. It's not accelerating. The reason why this particular object is not accelerating is because the weight of the object, which is pointing down, is equal to the tension which is in this rope, which is chord number 1. The tension which is in this rope, chord number 1, is pointing up this particular direction, like that. And with respect to this weight, okay, there is also other tensions. One which we get from this particular chord, which is chord number 2. So there is a tension in this particular rope which is pointing in this particular direction like this. So we have what we have here is we have got a tension in this rope, in the horizontal rope. We have got a tension in this vertical rope. We have got a tension in this one here. And with this particular setup, all these forces which are in these ropes have the end result of making this particular point P not to move. So with that information, we can try to find out what forces are acting on this particular point P. There is this one, which we have been told is 30 newtons. There is some other unknown force which is acting in this particular direction. There is other forces which are pointing this particular, which are acting in this particular direction. Okay, are we clear about that? About the fact that there are forces which are acting in these ropes?
Yes, sir.
Okay, so the other thing which we are going to be doing is, as you can see, there are these particular angles. There's a 40 degrees here, there's a 50 degrees here, and stuff like that. So basically, we need to have a uniform way of, apart from just us saying, okay, fine, this is how much force is living in this particular rope. We need to have a uniform way of giving direction. In what direction is this rope running? Okay, so we are going to be measuring direction from this particular rope. From this rope, then you're going to measure direction in an anti-clockwise direction. So we're going to be measuring our angles like this. Are we clear? From the we're going from this particular vertical. If we choose this to be our positive, this direction to be our positive x-axis, we're going to measure our angles in this particular direction. If we do that, then you notice that this particular rope chord number 2, is at an angle of this up to here, that's 90 degrees. 90 degrees plus 50, that is 140 degrees. So this particular rope here, up to here, it's an angle of 140 degrees. Then this particular rope here, if you count like that, that's 90 up to here, up to where it is, you're going to see that it's an angle of 270 degrees. Are we clear? Is it clear?
Yes, sir.
we will be measuring angles from this direction like this. So if we do that from here up to here, that's 90. 90 plus 50, that gives us 140 degrees for this chord. And that particular force which lives in this chord is going to be at an angle of 140 degrees. If you look at this particular one here, if we measure like this, that's going to be 90, then 180 up to somewhere here, another 90, we're going to have 270 degrees up to here. So using this information, we can find out what we can find out what are supposed to be the components of this particular tensions which live in these particular ropes. So we are going to start with, since we want to keep this particular point P motionless, we are going to start by designating the unknown force which lives in this particular chord to be T1. The other force which lives in this particular rope, we're going to call it T2. Then of course this other one, if we call it T or whatever it is, we know what the size is. The size is 30 degrees. Sorry, the size is 30 newtons. Okay, so when you do that, we are trying to find out how much force lives in this particular rope and how much force lives in that particular rope. So for each particular thing, so what we end up with is the following. We are going to create a table of components. So in this case, the force or the tension which lives in the first chord, in this particular chord, the first one, the tension living in this rope, the chord 1, we're going to call that T1. The tension which lives in this particular rope, we're going to call that T2. Then the tension which lives in this rope, we're going to call that T3. So this 30 newtons, we're going to call it T3. Then whatever force lives in this particular rope, we're going to call it T2. Whatever force is living in this particular rope, we're going to call it T3. The direction of the tension depends on where you are, from where you're interested in. In this particular point, if we are interested in this particular point, then the tension is pointing down. If you are interested in what's happening with this particular weight, then the tension is pointing up. Okay. So yes.
Before you proceed, I just want to ask why have you chosen 140 for the chord 2?
Why have I what?
Why have you chosen 140, like the angle 140 degrees?
Because I've chosen to measure angles from this rope. From this direction. Basically what I'm trying to do is I'm trying to put an XY plane at this particular, I'm trying to overlap this particular point P with an XY axis. So if I put an XY axis here, then it becomes obvious that this rope here, this 30 Newton rope, can act as my positive X axis, then the other things just fall in place, so that I can easily measure angles. Yeah. So you have a choice of choosing where you want to start measuring your angles from. And once you make that choice, you stick to it.
Okay.
Yeah. So when I do that, because of the choice I've made to say I'm going to measure angles from the horizontal rope, when I do that, I will end up with the following. I will end up having T1. This T1, whatever the size of T1 is, I don't know. But I know the X component, so I'll have to create a table of components like this. I'll know that the X component of T1 is going to be equals to what you have. What is T1 multiplied by the cosine of 270. Now, cos 270, if you have a calculator, turns out to be 0. So T1 times cos 270 is going to give you 0 newtons. So basically what this is telling you is that T1, the tension T1 does not have an X component because of the choice of angles, how we have decided to measure angles. Are we clear? Is it clear? T1 is the tension in this rope, chord 1. The tension which lives in this rope. You can see this rope is vertical. So if we choose this to be our x-axis, our positive x-axis, then this other side to be a negative x-axis, this becomes a y-axis, and this tension lies along the what's going to be our y-axis. Then there is no component of this particular force along the x-axis. Is that clear? Are we clear? T1 is whatever T1 is, the unknown value of T1, fine. Whatever T1 is multiplied by cos 270, this is going to give you 0 newtons. Then T1 sine 270, sine 270 is minus 1, so you're going to end up with minus T1. Is that clear? I need a response.
Yes, sir, it's clear.
Okay. Next, we move on to the other force, which I've called T2. T2 is the tension which lives in the second drop, this one here. If we choose to say we're going to be measuring our angles from this particular chord in this anticlockwise direction, then we see that the angle this one makes up to here is 140 degrees. If we measure our angles from this direction like this. So whatever the tension is in here, multiplied by, which is what you're calling T2, multiplied by the cosine or the sine of this 140 degrees. So when you do that, we're going to end up with the following. We're going to end up with T2 cos 140, which is going to be equals to minus 0.77 T2. Then this side also, we're going to have T2, the y component is going to be T2 sine 140, which is going to give us 0.64 T2. Is that clear? About T2? I need confirmation that people have understood what we're doing.
Yes, sir, it's clear.
Okay. Then, because of the choice of what we have made, when it comes to T3, we have said that we're going to be measuring our angles from this direction. From here. So if you look at what T3 is here, which is the 30 newtons, the angle it makes is 0 degrees. So it lies along, the reason why it's 0 degrees is because whatever the tension is here lies along the x-axis, the positive x-axis. So the angle is 0 degrees. The size of T3, which is 30 newtons, T3 is 30 newtons, but the angle it makes is 0 degrees. So we can find out what the x component is and how much the y component is supposed to be. So for T3, T3 is going to be whatever the size, T3, which is 30 newtons, multiplied by cos 0 degrees, which is going to give you 30 newtons. Then that's the x component. So basically, it's telling you that the whole thing lies along the x-axis. Then for the y component is going to be 30 newtons multiplied by sine 0 degrees. This is going to give you 0 newtons. So this is telling you that along the y-axis, the tension T3 does not have any component, but it only has components along the x-axis. Is that clear? These are the forces acting on the point we are interested in making sure that this point doesn't move, acting on this point P. These are the forces acting on the point P and their components P. In this particular setup, this point P remains motionless. So the reason why it remains motionless is because it's in equilibrium. So we enforce the first condition of equilibrium, and we have the forces acting on that particular point and their components. So once you create a table of components, the components of the tensions like we have done here, the next thing we need to do is we need to add the x components and make sure that they add up to 0. We also need to add the y components and you make sure that these y components add up to 0. The first force, T1, its component is 0. The second force, T2, its component is minus 0.77 T2. The other force, T3, the x component is 30 newtons. So we need to add 0 newtons plus this, then it should give us 0. We also need to add this, plus this, and the whole thing should give us 0. Are we clear? And that's what we try to do here. Here, we add the components of the forces along the x-axis, and when we do this should give us 0. So when you do that, when you add the forces, the x components of the forces, we're going to have 0 newtons plus minus 0.77 T2 plus 30 newtons, and that gives you 0. This 0, you add 0 to anything, whatever it is you get, then this bit here, this one here, we take it to the other side, so we end up with 0.77 T2 equals to 30 newtons. Then you divide by 0.77 to 30 divided by 0.77, you end up with T2 equals to 30 divided by 0.77, and this is going to give you approximately 39 newtons. So your T2, which is the tension in the second rope, is going to be 39 newtons. By applying these, the first condition of equilibrium, by adding the forces along the x-axis and making sure that those forces add up to 0. Are we clear?
Yes, sir.
Next, after we add the forces, or the x component of the forces, and make sure that they add up to 0, this is how we end up with this T2 equals to 39. We do the same thing for the forces acting along the y-axis. So along the y-axis, this is what you have. We have got T1, which is this, we have got T2, which is this, and you've got a 0, which is that. So we add minus T1 plus this plus that, and that's what you're trying to do with these. The sum of the forces along the y should be equal to 0, and the sum of the forces along the y, that's going to be minus T1, which is this, plus 0.64 T2, which is what you have here, plus 0 newtons equals to 0. And when you do that, you get this bit to the other side, you end up with T1 is equals to 0.64 T2. So this is how T1, which is the tension in the first rope, is related to the tension in the second rope. Like T1 is equal to 0.64 T2. But you remember that we have just worked out what T2 is here. T2 is 39 newtons. So we can find out how much T1 is. So T1 in this particular case is going to be T1 is equal to 0.64 times 39 newtons. Then you're going to end up with T1 being equals to 25 newtons. Is that clear?
Yes, sir. Sir,
Yes.
I've got another question.
Yes.
We have got the 40 degrees on just next to the code 2. So we cannot use that, like.
There's always more than one way of working out a problem.
Oh, okay.
Yeah. This is the simplest way I'm offering. Say you have to choose things like this. So if you've got another way of doing things, that's up to you. But as long as you enforce the first condition of equilibrium, then things should come out. If you enforce it properly, then things should come out.
Okay. Thank you very much.
What this thing is showing here, this 40 degrees here, what it's showing here is that if you do like this, what you call, is it alternating angles? This is 50. So it means for this side should be 40 because the whole thing should be 90 degrees. So that's what this 40 is here, showing you.
Okay.
Yeah. So now we know that the tension in this rope is 39, the tension in this rope is 25. That's what's keeping this point from moving. Now, when you're looking at it from this point, the tension in this rope is in this particular direction. But when you're looking at it from the point of this weight, the tension is pointing up. Otherwise, if there was no tension in this rope, this weight would fall off. Now, the fact that the weight is not falling off, and the weight stays the way it means that the weight of this particular object is equal to the tension which is in the rope code 1. Okay? If the weight of this particular object doesn't match if the tension in this rope does not match the weight of this thing, then this rope is going to break. So the fact that this particular mass is not accelerating downwards but it remains motionless, it means that the tension which has been generated in this rope is equal to the weight of the object, which is the weight of this thing which you have. So the weight of this particular object is going to be equal to the tension of this particular thing, because the rope will generate an amount of tension which is equal to the weight of the object. The reason why these ropes are arranging themselves like this is because of this weight. So we conclude that the weight of this object is equal to, in size, to the tension which is in code 1, and the tension which is in code 1 is what we have found to be 25 newtons. Yeah. The weight is equal to the tension in code 1, And if that's the case, we know that the tension equal to 1 is 25 newtons, therefore the weight will be equals to 25 newtons. Is that clear?
Yes, sir.
Okay, so that's how basically you proceed with that. So the first few examples in this particular case are examples of objects where we are applying equilibrium, the first condition of equilibrium, making sure that there is no acceleration. Okay, example number 2, in figure 2, a 50 Newton box is slid straight across the floor at constant speed by a force of 25 newtons. Now, when something is moving across the floor at constant speed, it means that that particular object has got no acceleration. Are we clear? That's the first thing which is supposed to come to mind. If something is moving at a constant speed, it means that there is no acceleration in this particular object. So the question is, how large a friction force impedes the motion of the box? And what else? How large is the normal force? So where is this particular box which we are interested in? Figure 2.
So it is down.
Yeah, it's down here. So we have, this is the arrangement which we have here. So we have a box like this. There is a force which is acting on this particular object. The force is acting at the force is 25 newtons, and there is an angle. So the force is acting at an angle. So this is how the object is being pulled. Okay. Then of course there is friction force which is in this particular direction, like this. Then there is a weight of the object, which is this one here. Then of course this particular object is exerting a weight on this floor, and the floor is not happy, so the floor is pushing back against the against the normal force, against the box. Now in this particular case, again, it is up to you to choose which one is going to be which. If I choose this direction, if I say this side is going to be the x-axis, then this side is going to be the negative x-axis. Then if I choose up to be the positive y-axis, then down is going to be the negative y-axis. Is that clear? If I choose the direction in which the box is moving, because it's sliding, the box is sliding like this. So if I choose the direction in which the box is moving to be the positive x-axis, then this side is going to be the negative x-axis. Then if I choose up to be positive, so that would be the positive y-axis, then down is going to be the negative y-axis. Are we clear? Is it clear? When you have an object moving like this, you choose the direction in which the object is moving to be your x-axis or your y-axis. So in this case, since the object does not move up and down, this is our y-axis. It's like you get what's this? You get your xy plane. You put your xy plane over this object. You draw an xy plane over this particular object. When you draw an xy plane over this particular object like this, if you choose this direction, up down to be your y-axis, then this left right is going to be your x-axis. So you draw an xy plane over this box. So the y-axis is going to be in this direction. Your x-axis is going to be in this direction. Are we clear?
Yes, sir.
The next thing you do is the direction in which the object is moving. This object is going to be moving in this direction. You choose that as your positive x-axis. So you put an xy plane over this object. Then the other thing you do is the direction in which this object is going to be moving. You choose that to be your positive x-axis. Are we clear?
Yes.
So if you choose that to be a positive x-axis, then we'll be measuring angles from the positive x-axis as we have agreed in this direction, anti-clockwise. You measure your angles like this, anti-clockwise. So in this case, when you measure an angle like this, you see that this force, 25 newtons, is acting at an angle of 40 degrees. So you can work out what is the x component of this force, F. You can find out what is Fx, Fy. Then you come to this force, the friction force. You can find out what is the x component of the friction force, what is the y component of the friction force. Clearly, if we are choosing measuring angles from this line, you can see here, then this bit here is going to, the angle from here to there is going to be 180 degrees. So for the friction, the angle is going to be 180 degrees. For this particular force, the weight of the box is in this direction. So you're going to measure your angle like this. That's going to be 270 degrees. For this other force here, it's pointing up like this. So the angle is going to be 90 degrees for this. Are we clear? The way this angle is being measured like this, say this angle is 40 degrees. We're measuring from this line. From this same line, you can also measure other angles. You can measure what the angle for this one is. That's going to be 180 degrees. You can also measure what this angle makes from this particular direction. That's going to be 90 degrees. And this other one here, this one makes an angle of, from this line here, in this direction, of 270 degrees. Is that clear? Over this box, you draw an XY plane. Then it will become clear that, okay, this line, because when you draw an XY plane here, when you put an XY plane here, okay, when you put an XY plane here, remember what these things are. This is a force. This is a force. This is a force. This is the force. These forces are vectors. A vector has got size, and a vector has got direction. So as long as the size of the vector is the same, as long as the direction in which the vector is pointing is the same, then it doesn't really matter. You're talking about the same thing. You can shift. When you draw your XY plane, you say, okay, x-axis, y-axis, then you draw your XY plane over these things. These forces, you can lift them. You can lift this 25 newtons. You come and put it at the origin, so you can have your force nicely. You can lift this one. You put it, connect it to the origin. This one you connect it to the origin. This one you connect to the origin. As long as the direction of the force is the same, as long as the size of the force is the same, then you're talking about the same force. Are we clear? Is it clear? I'm not receiving any response. Okay, so if you draw an XY plane, you get a pencil, you print these notes, then you get a pencil, you draw an XY plane over this box. Then you shift this 25 with this force, you maintain the size, you connect it to the origin, then you make sure the angle is the same. Then this other side, you get this, you connect it to the origin, you make sure the direction is looking the same. You get this, you connect it to the origin, you get this, you put it on top, you connect it like that. You can lift these forces, you can put them in different places as long as these forces are pointing the same direction and the size of the direction of the forces is the same, then you have not changed anything. So with this, we see that this particular force of 25 newtons makes an angle of 40 degrees. This other force, the friction force, makes an angle of 180 degrees. This one, the normal force, whatever it is, it makes an angle of 90 degrees from this line, from the x-axis. This one, which is the weight of the box, makes an angle of 270 degrees. So with that, you will make what's referred to as a table of components for the forces acting on the box which is being pulled. The first one is, of course, is the force which you are pulling the box with. So that's going to be the tension in the rope multiplied by the angle, the cosine of the angle, which is 40 degrees. We know that the tension is 25 newtons. 25 newtons times cos 40 degrees, that's going to give you 19.2 newtons. Are we clear?
Yes, sir.
Then So that is the x component, how much the tension of the rope is along the x-axis. You also work out the y component. The y component is going to be the tension in the rope multiplied by the sine 40. You know that the tension is 25, so 25 newtons times sine 40, that's going to give you 16.1 newtons, like that. So the tension in the rope, this tension which is pulling this box, the x component of this tension is what we have found. 15 newtons times cos 40 degrees. The y component is 15 newtons times sine 40 degrees, and that's what we have put in this table here. Say the x component is 19.2 newtons, the y component is 16.1 newtons. Then there is the other force, which is this one, the friction force. Whatever the size of the friction force makes an angle of 180 degrees. It's always opposing the movement of a particular object. So in this case, friction force is going to be equals to, which is what you have here, the friction force. So the x component of the friction force is going to be the friction force, whatever the friction force is, multiplied by the cosine of 180 degrees, and that's going to give you minus F. So friction, the x component of friction is a negative of whatever the friction is. The negative is showing you that it opposes your motion of the particular thing. Then the y component of the friction is going to be the friction force multiplied by sine 180 degrees, and that's going to give you 0 degrees. So this is telling you that friction does not have a vertical component. Friction is only along the x component. Are we clear? Is it clear?
Yes.
Then you look at the normal force. The normal force is pointing up, and from what we have seen in that particular diagram, it makes an angle of 90 degrees. So whatever the normal force is, multiplied by the cosine of 90 degrees, you get 0 degrees. So basically this is telling you that the normal force does not have an x component. On the other hand, for the y component, whatever the normal force is times 90 degrees, it's going to give you Fn. So the normal force has got a component, and that's Fn. Then when you look at the weight of the box, the weight of the box is acting at an angle of 270 degrees. So that's going to be the weight of the box times cosine of 270 degrees. That's going to give you 0. So this is telling you that the weight of the box does not have an x component. However, because of how we have decided to draw an xy plane over the box, and we have chosen the direction in which the box is moving to be our positive x-axis, then it turns out that if we do that, then the weight is going to be at an angle of 270 degrees. So we say Fn sine 270 degrees, we're going to end up with a weight which is equals to minus Fw. So for each of the forces acting, this box is moving. So what we have here is a problem of not static. It's not a problem of static equilibrium, but it's a problem of kinetic equilibrium, where something is moving, but this particular thing is moving at a constant velocity. And that's what we have in this particular problem. So this is not a static equilibrium problem, but a kinetic equilibrium problem. So in this particular case, what we end up doing, so now that we have got our table of components, so you always need to come up with this table where you've got the vector, then the x component, and the y component, where you identify your forces, and for each force you find out what is the x component, what is the y component of that particular force. After you are sure, okay, fine, these are the forces, then these are the components, and these are the x components, these are the y components, then the next thing you have to do is you need to add the x components, the 9.2, 19.2, plus this, plus this, plus this. When you add them, they should give you 0, which is what is being done here. Here, the sum of the forces along the x-axis should give you 0. Then you also need to add the forces along the y-axis. Your 16.1 plus this, plus this, plus this, they should give you 0. Okay, so when you do that, so in this particular case, when you add the forces along the x-axis, so along the x-axis, when you add the forces along the x-axis, so the sum of the forces along the x-axis should be 0. So the forces we have, the components of we have this, 19.2 plus minus F plus this, that should give us 0. So you've got 19.2 newtons plus minus F newtons plus 0 newtons plus this newtons, that should give you 0. So this 0, 0 guys, they give you 0. So basically what we have here is 19.2 newtons minus F equals to 0. So we end up having friction force being equals to 19.2 newtons. That's how we get our friction force. So our friction force in this particular case is 19.2 newtons by applying this first condition of equilibrium. Are we clear?
Yes, sir.
Next, we are being asked to find, now that we know the friction, that's good. So the friction is known. You can also do it this side, except what is it? I don't know if you're going to get something very useful. You can add these guys up. But I don't think it's necessary for us to do that with the question we're being asked. We can add these guys up. 16 plus 1 plus 0 plus this plus this. So you can get some relationship about what the weight is supposed to be and stuff like that. So let's see what you have. So the other question says, how large is the normal force? Now for us to find out how large the normal force is, you can see the normal force is this side. We need to add our y components. That's what we need to do. We need to add our y components. And I think we have been told the weight of this box. What is the weight or the mass we've been told? Yeah, we've been told the box has got a weight of this much, 50 newtons. So the weight of the box is known. It's 50 newtons. Okay, so in that case, for us to find out what is the normal force, so we add everything along the y-axis, along the y direction, the sum of the forces along the y direction. So we have got the first one from the table of components is this one, 16.1 plus this plus this plus this. When you do that, we end up with the following. We have got 16.1 newtons plus 0 newtons plus minus Fw plus Fn, which equals to 0. And when you do that, you have got 16.1 newtons plus 0 minus 50 newtons. I'm replacing the Fw because I've been given is 50 newtons. I end up with minus 50 newtons here plus Fn equals to 0. So you have this bit, 16.1 newtons plus 0 minus 50 newtons. You're going to end up with minus 33.9 newtons plus Fn equals to 0. Okay, therefore, when you do that, you're going to end up with Fn equals to 33.9 newtons. Is that clear? Which is your normal force.
Yes.
So we now know what the friction force is. This is a friction force. We know this is the normal force. Then, the next question says, what is the coefficient of kinetic friction between the box and the floor? Now, for the coefficient of kinetic friction, yes, there is friction because this box is moving. Now we know that with kinetic friction, F friction is given by the coefficient of kinetic friction multiplied by the normal force. We know how much this is. We've worked it out. We have just also worked out how much this is. Therefore, the coefficient of friction is going to be equals to the friction force divided by the normal force. And the friction force in this particular case, we have found it to be 19.2 newtons. And our normal force, we have found it to be 3.9 newtons. Therefore, our coefficient of friction is going to be 0.57 newtons. Is that clear?
Clear, sir.
Yeah.
Yes.
So basically, that's how you use your table to find your friction. You use your table also to find your normal force. The friction is in this particular column. So you add up these x component terms here. The normal force is in this particular column, so you just add up everything and you work out what the normal force is. When it comes to finding the coefficient of friction, you just use the fact that the friction force is equal to the coefficient of friction multiplied by the normal force, then you work out what the friction is supposed to be. Okay. Is the game becoming clear on what we are doing? Is it becoming clear on what it is supposed to be done and how we are doing things? You have to identify what object it is, then you draw an XY plane over this particular object, then you choose the direction. If the object is not moving, like in our first example where the point P was not moving, you can choose anything to be your positive X direction. But if, like in this particular example, where an object is moving in a particular direction, you choose the direction in which the object is moving to be your positive X-axis, then you start measuring angles from that direction, from the positive X-axis, then you create your table of components. After creating your table of components, then you work out what the components are. Then after you work out what the components are, then you add those X components, you add the Y components, you make sure when you add them, they add up to 0. So you force them to become equals to 0. Are we clear? Then you find whatever it is we're asking you to find. So with example number 3, an object in figure 3 is in equilibrium, find the normal force Fn. So I don't know what, let's see, figure number 3. Okay, here, so this is what we have as, so this particular object is on an incline. Okay, now, if an object is on an incline like this, one of the things it's supposed to, this particular object has got weight. The weight of this particular object is at this, in this particular direction, like this. Then what else? This particular object is exerting a weight on this incline. The incline is pushing back against this force Fn. So this one here is the weight of the object. This one here is the reaction of the incline pushing back against this particular box. Then of course, I think this box is supposed to be slide. It will try to slide in this particular direction, but since it's at an equilibrium, it's not moving. So the box is kind of, we can say the box is stationary. If the box is stationary, that's okay. Then there is this other force in this particular direction trying to pull the box or stop it from moving, which is the friction force. So you've got the friction force, then of course you have the weight of the box in this particular direction. We know that this particular weight of the box has got a part of it which is trying to move the box this direction, and a part of it which is trying to exert a force in this particular direction. This one here, this weight you have seen here, this weight here, this bit here has been split. There is this which is down here. This is a component of this weight in this direction. There is also this line. This is the Y component of the weight. So this thing here has got two components. It has got this one, which is pulling the box down. It's this one pulling the box down. So since it's a force, it's a vector, I can lift this, I can put it here. So this is the one which is pulling the box down, and it's being opposed by this one. Then there is also this other component here, this bit here. This component is the one exerting weight at 90 degrees to the surface, and the surface is not happy about this, the incline is not happy about this, so the incline is pushing back against things. So what you notice here, basically, one of the things you notice here is that in a way, if this angle is known, this particular box weight, which is 200, has been split for you. There is this component which has been given to you. There is also the other component which has been given to you. That's one way of doing things if you want to do them like that. What other information do we have about this problem? Okay, so the object in figure 3 is in equilibrium, find the normal force. Is that the only information we have? Okay, so if that's the only information we have, then that's fine. So we're going to use the fact that we can split the weight. You've seen this weight? We can split this weight into this component. This is going to be our, so we're going to choose this box. When it slides, it will most likely slide in this particular direction. Okay, so in this box slides, it slides. So we're going to choose this direction to be our positive X direction. We choose the direction. You can put an XY plane over this thing. You draw an XY plane over this box, then the direction in which this particular box is going to slide, which is this direction, or the direction in which the box will tend to move, that will become our positive X-axis. So if we do that, our positive x-axis is like this. Then this bit here, this is going to become our, this will become our x-axis. Then this will become our y-axis. So for the weight, if we pick the weight, I write down things properly here. The x-axis is not going to, I think I've made a mistake here. I think I've made a mistake. 200, this is 200 sine. It's supposed to be sine here. I think this one I've made a mistake here. Because this bit here, this side, this bit with this angle here, this is 200 sine theta. Then this other side here is 200 cos theta. So what this, so this is supposed to be here, and the other thing here is supposed to be what you're supposed to put here. This bit here is 200 sine theta. This bit here is 200 cos theta. Are we clear? This side here, which is the x component, which is the y component, this is 200 cos theta. This bit here is 200 sine theta. So here they have been, I will need to make I think I need to make another correction where I switch them this side and this side. Apart from that, the normal force. So if we measure our angles from this particular direction, if we measure our angles from this direction, so our normal force will be pointing up. That's going to be 90 degrees. So if you're measuring from the direction in which the box is going to be moving in this direction, if the box moves in this direction, then our, what is our angle like that, our angle like that is going to be 90 degrees from this side. If we choose this to be our positive x direction, so our angle in this particular direction, from here up to this, where this guy is pointing, that's going to be 90 degrees. Then where this guy is pointing, that's going to be 180 degrees. Then where this one is pointing, that's going to be what? Yeah, I think I probably made some confusion and stuff like that. Let's see. So this is Fn cos 90, so 0 degrees. Fn's are 90, that's Fn. These other bits, F cos 0 degrees. This, and what choice did I make? Okay, let me see. We choose the direction parallel to the incline to the x-axis. And so we parallel to the incline, that's what we choose to be our x-axis. Then, and the direction perpendicular to the incline, that's our y-axis. The box exerts a weight of 200 newtons on an incline at an angle theta. The incline is not happy about this, so it pushes. Okay, yeah, that's where the normal force comes in. The weight of the box has got two components, x and y directions. The components of the weight along the y direction is counter balanced by the normal force, yes. The components of the weight along the x direction is countered, okay, but that stays motionless. This information is presented in that table like this. So but something is not correct. I'm not happy about how these okay, 200 cos theta. If I do that, the question is, where am I measuring the angles from? If I do that, 200 cos theta, where am I measuring theta from? Because for this one, which is pointing up like this, whether I measure the angle from this side or from this side, it's still the same thing. It's going to be 90 degrees. Now, for the friction force, I've written cos 0 degrees, which seems to imply that I am measuring an angle from this side, like this. So if this is 0, like that, then if this is 0, I measure from here 0, then like this. Okay, I think you could be fine a bit, but I'm not sure exactly if we're fine if we did that. So if this is 0, if along this line, if this is 0, then this one is pointing up, that's going to be 90. Then I'm going to end up measuring like this up to here. Are we clear? If I measure from, okay, fine, yeah, I think we might have something, we might be onto something. If I measure from this line, if I say, okay, fine, I will put an XY plane over this box. Are we clear? Over this incline. Then I measure from this to be I take this side to be my positive x-axis. So the angles from this line will be 0 degrees. Then when it comes here, for this one, it's going to be 90 degrees. Then when it comes here, whatever the angle is, it's going to be a certain theta, but not the one which have been given here. What we know in that particular case is that if I do from this all the way up to here, if I go around like this all the way up to here, I'll end up with 270. But I'm not yet at 270 because I'm ending up here. I'm ending up here. That's why I'm ending up. So let me see what we get. So I think it's fine with what I've done, except the theta which I have. It's not this theta. It's the theta from like this, measured from here all the way up to here, which is a bit confusing in this particular case. So we end up with FW, which is 200 cos theta, then 200n sin theta. We don't know what the theta is. We measured from this side, like this, all the way up to here. If we choose this to be the positive x, then this bit will be the negative x. Okay, so for then Fn, you're going to have Fn cos 90, which is just nothing, 0 degrees. Along the x, Fn sin 90, which is going to be Fn. Then this bit, Ff cos 0 degrees, that's going to be Ff. Then this Ff sin that is going to be that. So these are the forces we can identify. If we add this, what we have here, this plus this plus this, then you add this plus this plus this. So what we end up having is, when you add the forces along the x-axis, you've got this bit here, 200 cos theta. Then you've got this one here plus this one here. So we end up having 200 cos theta plus 0 degrees plus F. That's going to be 0. So we end up having the friction force being equals to minus 200 cos theta. Then if you do the same thing along the y direction, 200 sin theta plus this plus that. So you end up having, along the y direction, you're going to have 200 sin theta plus Fn plus this bit equals to 0. So we end up with, so we have this bit here. You end up with Fn equals to 200 something. Fn is equals to minus 200. But this does not answer my question, because I still don't know what the theta is. So I think there's something wrong with my approach. What else can we do? I think in this particular case, things would have been easier to find if we knew what the angle is. With what we have done, because we need to know what the angle theta is, but since we don't know anything, can we do anything? Can we do something else? So right here, there is a friction force which you don't know. Then of course there is theta which you don't know. That's two things you don't know. Then there is also the other bits. Fn, we don't know what Fn is. So there are three things which you don't know. So in this particular case, we will need to be given we need to be given what theta is. But in this case, I think my approach here is not correct. Basically, it would have been better if I picked these guys. If I pick the components, if I pick these components, if I use this component and use these components, then things would have been much better. I need to probably between now and when we meet on Thursday, I need to rewrite this bit here, where I try to use these components. I know this bit is 200 FW sine theta, so I know this bit. This is the x component. This bit is 200 cos theta. So let me try to use these components, this and we use this and that, and see how it tries to come out, even if we don't know what the angle theta is. Okay, so I think we'll stop here. Let me try to redo this from a different, different perspective, and see if we get something which makes more sense.
So,
yes.
I just want to ask on these the weight components. Where we have got x component, which is cos. Like when we're dealing with vectors, we thought say when we are in the x direction, we always use cos, and y we always use sine. I don't know if we are going to stick to that.
No, we're not going to stick to we can't stick to that, because this thing has been raised by an angle theta. If you get raised by an angle theta, then the component, the x direction is this. So from this angle theta is the same as this angle theta here. So when you do that, you can treat this as a triangle. So when you do that, then this is your x component. So this becomes whatever 200, it becomes your x component, which is this, becomes 200 sine theta. Then your y component, which is this, is 200 cos theta. So when you raise when your surface is raised a bit, then the normal way of doing things switches. Are we clear?
Yes, sir.
Yeah, so I think I need to do that. Okay. Any other question?
Yes.
Okay. If there are no other questions, then we'll come back to this particular question when you meet on Thursday. But I'll need to do a rework of this question so that this approach which I took here can be addressed. Okay. Unless there's another question, since we spent some time watching the president speak, that's why we have gone a bit over time. So we can stop now, unless people have got questions. If you don't have any questions, then see you on Thursday.